Swayam Prabha. Digital India. Educated India.
So we're going to now discuss some common discrete probability distributions. The first one is geometric distribution. We'll start with an example. Suppose an auto pisher in a ring frame has a success rate of 0.4 while trying to piece an end break. On the ring spinning machine, as we spin the yarn may break at any point of time, which is unpredictable when it is going to break on a particular spindle. And therefore, what we have nowadays that there is a piecing device called auto piecer, which keeps on traveling. And whenever it finds that there is a break, it stops there and it mends the break. So it is called auto piecer. So it keeps on patrolling, and whenever it finds there is a spindle not running because yarn is not being produced, which is broken, it is going to piece, that is join the yarn, and it will start spinning again. So, but its success rate is 0.4. It attempts to piece, but it fails sometimes. So, probability of success is 0.4. Now, what is the probability that it will succeed to mend the break on third attempt? So, if it fails, it tries again. If it fails again, it tries again. So, it can go 2, 3, 4, 5 times also sometimes. So, now the question is that what is the probability that it will succeed on third attempt? How do we approach this problem logically? So, probability of success in an attempt is 0.4. So, probability of failure is 1 minus 0.4, 0.6. If the auto pisher has to succeed in the third attempt, the first two attempts must be failure. Hence, the probability of succeeding in third attempt will be probability of failure in first attempt, probability of failure in the second attempt, multiply the probability of success in the third attempt. So each probabilities will be multiplied here. It follows multiplication rule, because the probability of success or failure in a given attempt does not depend what happened in the earlier attempt. So they are independent to each other, and hence to find out that they will be definitely going to be failure in the first two attempts and succeed or success in the third attempt, each probabilities we need to know and then multiply them. So P of F into P of F into P of S, and P of S we know, P of F and S are known to us, so we just put those values and multiply them, we get a figure 0.144. So that becomes my probability that it will succeed in the third attempt. So geometric distribution, that means if I generalize it now, suppose a trial has two outcomes, success or failure. Let the probability of success in any single trial is constant, and that is what is P. Now imagine succession of independent trials. Every trial is independent to each other. The probability that the first success will occur on kth trial will be that is probability X is going to be K. Kth time it is going to be successful. will be, there has to be a failure k minus 1 times earlier, and on the kth time there has to be success only. So you have k minus 1 time failures which will precede the success that is going to occur on the kth trial. And if I write these probabilities, failure probability is 1 minus p, 1 minus p, 1 minus p, 1 minus p. How many times? K minus 1 times. And success on the kth time is going to be p. So it is going to be 1 minus p to the power k minus 1 into p. That is going to be my actual value. Px is going to be k. So this is very simple. Px equal to k is 1 minus p to the power k minus 1 into p. That becomes a very simple formula. The distribution is completely defined when p is known. And the mean and standard deviations of geometric distributions are, mean is 1 upon p and standard deviation is root over 1 minus p by p. This can be proved, but we are not going to prove them here, just to save some time. So these proofs are not required. You need to remember that for geometric distribution, the mathematical expression is this: Px equal to k is 1 minus p to the power k minus 1 into p, and the mean is always 1 upon p, and standard deviation is root over 1 upon 1 minus p by p. Or we can 1 minus p I can write is by q, or failure, whatever we generally p is success, so q is failure. That's what generally it is written. But this is what it can be. We can write that mean is this and standard deviation is this for geometric distribution. It's a very, very simple type of distribution. Then we come to binomial distribution. Binomial distribution is more, you can say, common. And again, we start with an example. Let us say shards are produced in an assembly line is classified as defective and non-defective. Suppose 3 shards are chosen at random from a day's production. We are choosing just 3 shards. What are the possible outcomes? These are the possible outcomes which are written here. D means defective and N means non-defective. So all the 3 could be defective, so it could be D, D, D. Or it could be DDN, DND, NDD. They are all written, no, they are all shown by one particular color, because in all these cases, D appears twice. But these are the different ways it can appear. The outcome could be DDN or DND or NDD. Similarly, the outcome also could be NND, NDN, DNN, where we find 2 times N is appearing. And another possibility is NNN. All 3 are non-defective. So these are the possible outcomes. These possible outcomes are known as sample space. So we say sample space is basically the possible outcomes. We represent it by generally S. We write like this and say this is my sample space. Suppose the probability of defective is 0.2 and therefore non-defective is 0.8. All right. Now, probability associated with each of those outcomes we want to calculate. For the very first, all defective, D, 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 the probability is D is 0.2. So that means 0.2 into 0.2 into 0.2. So it will be 0.2 to the power cube. The next outcome, DDN, is 2 times effective, 0.2 to the power squared into 0.8. Second one is also same. D and D also same, 0.2 to the power squared, 0.8. The third one also is same, 0.2 to the power squared, 0.8, because in all the cases D is appearing twice. And 0.2 is the probability that shot is going to be defective. Therefore, 0.2 to the power squared basically means 0.2 into 0.2. The other outcomes probabilities are 0.8 square into 0.2, 0.8 square into 0.2, 0.8 square into 0.2, because in all these squares non-defective is appearing twice. So these are the probabilities for each individual outcome, and for the last it is 0.8 cube. So outcome wise probabilities are calculated and shown here. But most of the time the interest is not in individual outcome, but on how many defectives were found irrespective of the order. That is what we will be mostly interested. Out of 3, how many defectives can be found? Not in which order they were found. We want to know the random variable x, which assigns to each outcome the number of defective founds. Whether I have found 1, 0, or 1, or 2, or 3 defectives. So if x is the variable which is assigning to each outcome the number of defectives found, then x can have values 0, 1, 2, 3. So x is 0 if and only if n and n occurs. X is 1 if and only if these 3 outcomes occur. X is 2, x is 3, the corresponding outcomes are shown. And p equal to 0, that is px equal to 0 is 0.8 to the power cube. That is, you will have 0 defectives. That means all of them will be non-defective shots. So it will be 0.8 into 0.8 into 0.8. So probability x equal to 0 is going to be this much. Probability that you will get 1 defective, 2 defective, 3 defective, that is same thing we are writing as P capital X equal to 3. These are the corresponding values which we have already calculated earlier, but it is written now in a different format. So you can say these are the corresponding probabilities that I will have 0 defective shot, or 1 defective shot, or 2 or 3 defective shots. That was an example of typical binomial distributions. Now if you write in a generalized way, binomial distribution is concerned with the sequence of independent trials. If you remember, the trials are independent always, where the probability of success in each trial is equal to P. That is very important. And there are only 2 possible outcomes, defectives or non-defective, or it could be success or failure. Like in an exam, the students can either pass or fail. There is no other outcome. Something could be good or bad. So probability of success is same in each trial. Outcomes from different trials are independent, and fixed number of trials are conducted. So this must be satisfied. Assuming that all these are satisfied, then only we can say that binomial distribution can be applied. Now let us say n trials are carried out binomial distribution gives the probability of getting k success in n trials. And let x denote the number of success in n independent trials. So one typical outcome could be success, success, success coming k times, followed by failure n minus k times. Because there are n number of independent trials are carried out. So if there are k success, and this may be a typical order which is shown, initially all consecutively successes are coming k times. The rest are all failures. So this could be a typical outcome or order of the outcome. Since all repetitions are independent, the probability of this particular sequence is success is k times p to the power k and failure is n minus k times. So 1 minus p to the power n minus k. And we multiply these two because they are all independent events. There will be many other outcomes for which x is going to be k. This is one particular order, but there could be another order in which k times s will be found. So there will be how many orders could be there in which in all those outcome orders we will find k times s. That is the combination of n and k. That is n c k will give you that figure. That so many orders could be there in the outcome in which k times s can be seen when I am going for n number of trials. And therefore, the probability of getting x equal to k, that is success to be k times, is n c k into p to the power k into 1 minus p to the power n minus k. And n c k is shown here as factorial n by factorial r, factorial n minus k multiplied by p to the power k, 1 minus p to the power n minus k. So this is the mathematical, you can say, expression for calculating the probability that the variable x is going to take a value k. That is, in n number of trials I will get k success. And if you look at this final expression, we find only two parameters. One is n and the other one is, sorry, three parameters you can say. P, n are the two important parameters, and k is going to change. K could be 0, could be 1, could be 2, or 3. So the parameters wise, parameters are n and p of the distributions. And number of defects that we can see, that will could be, that is the value k. So k can take different values. K, but obviously the maximum value of k could be only the n. It cannot be beyond n. It cannot go beyond n. And the mean for binomial distribution is np, and standard deviation is np into 1 minus p. Also, that could be, we can prove them also. There are proofs available in some textbooks. If you are more keen to learn that, then you have to read those derivations where they have actually found out the value of mean and value of standard deviation. How these expressions are there in some textbooks, but we are not going to prove that. So you have to simply remember that mean is this and standard deviation is expression is this. NP and 1 minus P is basically Q, we can write failure. So it simply it is root over NPQ. So mean is NP and standard deviation is root over NPQ. Now again we are choosing an example. It is known that let us say 5% of the shirts made in an assembly line are defective. If hundreds are chosen, 100 shirts are chosen, what will be the probability that 2 shirts will be defective? Solution, if we go, what is the value of P here? Is given 5%. So 5% basically means 5 by 100. It is 0.05. And we are choosing 100, one after the other. So N is going to be 100 here. And we are interested in knowing how 2 shirts, probability of 2 shirts becoming defective out of that 100 that we have chosen. So K value here is actually 2. So it is as if 100 independent trials, there is a huge lot of shirts which are there, and we are choosing 100, let us say randomly, and from in that 100 we will expect probability of getting 2 shirts which are defective. We know that in the entire population 5% of the shirts are be always defective. So P value, N and K are now given. We have to simply straight away apply the formula. So write the formula, put the values of P, N and K. And if we do this, we get a figure this final. This is the value that you will get. That probability of getting 2 shirts defective is going to be 0.08. Now if we do the similar problem, now if we take these values, put them into Excel, and you keep changing the value up to K. K, let's say I have found out K for only one value. K when K is 2. I can find out for K equal to 0, K equal to 1, K2, K3, K4, K equal to 5, K equal to 10. And we can get all those probabilities we can calculate easily using the binomial function in the Excel. So all those mathematical or the manual calculation using calculator will not be required. The next distribution which is important is Poisson distributions. Now there are situations when events occur randomly over length, over area, over volume or time. And there is theoretically no limit to the number of events that can happen in a trial or in a unit. Now it will be clear if we go to the examples. There's a number of faults in 100 meter of yarn or 1000 meter of yarn. So over the length of 100 meter or 1000 meter, the faults are there. Faults could be, there's no limit how many faults could be there. It could be 5, it could be 10, it could be 50. If the yarn is very poor, it could be 1000 also. Theoretically, there is no limit. Number of end breaks in 1 hour in a spinning machine, or number of defects in a square meter of fabric, or 10 square meter of fabric, or in a fabric roll. In all this, these are the typical cases where Poisson distribution will be applicable. If the events occur independently and one at a time, low limit to the number of events that can happen. The appropriate distribution that describe this kind of phenomena is Poisson distributions. In the Poisson distribution, the variable x is the number of events per unit time or space can take values which could be 0, 1, 2, 3, 4, 5. So number of faults in that 100 meter of yarn could be 0, no fault. Or it could be 1, it could be 2, 3, it could be 10, it could be 50 also. So number of events per unit time or per unit space can take values, these values 0, 1, 2, 3, 4, 5, 6. So they are all basically integer values. And mathematical expressions for the Poisson distribution probability that exactly k event will occur, that px is going to be k, this is the expression e to the power minus lambda, lambda to the power k by factorial k. This expression you should also remember. And the mean for Poisson distribution is the parameter lambda. So whatever is the mean of the distribution, that is the value of lambda here. And standard deviation of this distribution is root over lambda. So Poisson distribution is a very unique distribution represented by only one parameter. And whatever is the mean, under root mean is the standard deviation. Or you can say mean and variance are same. Square of standard deviation is lambda. Mean is also lambda. Therefore, we can say that Poisson distributions, mean and variances are same. And if we want to find out the value of the variable that x is going to take k, k could be 0, 1, 2, 3, 4, 5, whatever, we have to use this mathematical expression to get the value. Now we are using this, let us say, in an example. A sewing machine breaks down 10 times in 50 weeks. What is the probability that the machine will operate without breakdown for 3 consecutive weeks? So 10 times in 50 weeks, that is the record that we have from our past data. So average breakdown per week is going to be 10 by 50, which is 0.2. So we need to know now what is the probability that there is not going to be breakdown in a given week. First week, then the second week, then the third week, because we need to know consecutive 3 weeks, it will not break down. There will not be a breakdown. So if we know, first of all, we need to know no breakdown possibility in the first week. We know the formula, Poisson distributions. Straight away, as if the value k is equal to 0 in this case, lambda is this, and k is 0. If we put these values, we get a figure 0.8187. That possibility of not getting, there's not going to be a breakdown in a particular week is 0.81. Breakage rate is independent of week, and therefore no breakdown in 3 consecutive weeks will be multiplication of the probabilities. 0.8187, 0.8187 to 0.8187, and that gives a figure 0.5488. So almost, let us say, 54.8% chance that there is not going to be a breakdown for consecutive 3 weeks. And this calculation I am just showing you an example. This is directly taken from the Excel. On the Excel, you have to go and to statistical functions which are there. If you choose Poisson distribution, Poisson.district dist, you will get this window. Now before that, you must have a column in which, suppose the column A1, the very first column, A1, A, B, C, D is there. Now here in this column you put these values 0, 1, 2, 3, 4, 5, because I want to change K from 0, 0 to 1, 1 to 2. I just want to know. So these are the values. Now in this particular window you have to input these values. What are the inputs? Main inputs is mean is coming. So mean is 0.2, the input of mean will be 0.2 here. The cumulative probabilities we are not going to find out, so we put a value 0 here. And then at the X, you have to write the column in which these topmost values that we have quoted. And if that is the first column, you just write A1. So this is the A1 cell data, which is 0. That is, 1 stands for the first row. So this is the first row, this is the second row, this is the third row, this is the fourth row, this is the fifth row, this is the sixth row. Say 1, you plot it. And for that, it gives you a figure 0.81. So in this particular case, when I put this value for K equal to 0, it gives a figure 0.81. See, same figure is here. This figure I have brought it here. Same value, I put it here. The moment I change, and if you copy that formula, and then you go to the rest of the rows, these are the values it will be generated. So the calculation will be done within no time. You get the various probabilities. Probability that you will have 0, you have 2, 1, 2, 3, 4, 5 breakdowns. So getting 5 breakdowns is very, very rare, not 10 to the power minus 6. 4 is also coming 10 to the power minus 6. So they are very, very low values. So this is how we can get the figure. Now, if we want to plot it for visualization, we can take this data and make a histogram also, just to see how the probability, once we plot them, how does it look. So that can be done. So this is how the Excels can be used to do many more calculations. And the last one is hypergeometric distributions. In both binomial and hypergeometric distributions, we are interested in knowing the number of events of interest in a sample containing n observations. So there is a lot of similarity between binomial and hypergeometric distributions. There is a little difference between them, and that difference is, you will be seeing here. In binomial, the samples are selected with replacement from finite populations. Or without replacement from infinite populations. Thus, the probability of an event, success or failure, is always constant, because the population size is not going to change. Or the population is so huge that if I go for without, if you replace this, it will not make much of a difference. outcome is independent of any other or each other. That means the outcome of present experiment or present trial will not depend on what has happened earlier. When it comes to hypergeometric distributions, in many ways there is similarity. For hypergeometric distribution, the samples are selected without replacement from finite population. So here it was with replacement from finite population, here it is without. This is one of the difference. Second thing is that the probability of any event of interest is not constant. Where it was stated here, it is constant. There is a difference between these two. And due to the same thing, outcome is dependent on the previous observations. So they are not independent, like it is here, this is not there. So this is the difference between binomial and hypergeometry. But we may have similar situation in some, in our, we'll see that in textile operations. Now, if you generalize this, suppose there is a lot of cones. So there, let us say there's a lot of 1,000 cones or 5,000 cones or cheeses containing yarns. So total number of cones are n. And out of that total number, defective cones are, let us say, r. And non-defective will be therefore capital minus r. Now this is situation. We know that this lot is going to be dispatched to some customer. Now n items are chosen at random from the lot. So we choose n items here, it is shown here. Without replacement. What will be probability that x is going to be k? Right? K is the number of defectives. Suppose in this n item that I draw from this lot, k defectives are found, so non-defectives will be n minus k. So actual population is capital N. It's a lot, but the samples drawn may be, let us say, 50, whereas the value of capital N may be 5,000. And we know that there are some cones which are defective, but they are mixed, so we do not know their locations, where they are. And we choose a small sample, which is size is small n. And in that sample, what can happen? There will be some defective and some non-defective ones. So k defectives, and therefore n minus k will be defective ones. So probability that x is going to be k if and only if we obtain precisely k defective items from r defectives in the lot. In the lot there are r defectives. So from here I have to get k defective items. Total defective items are all, and we have to get k. And precisely n minus k non-defective items from n minus r non-defective the lot. So non-defective are there. From there I have to get this. Then x is going to be k if and only this thing happens. So k defective cones can be chosen out of r defectives in RCK ways. And n minus k non-defective items can be chosen in capital N minus r and small n minus k different ways. These are the combinations. So K defective cones and N minus K non-defective cones. This will be non-defective. Can be chosen in this multiplied by this so many ways. And finally, small n cones can be chosen from capital N cones NCN ways. Therefore, probability of getting K defective cones while choosing small n cones is going to be this. This expression is this. So probability number of ways of getting K defective cones from R defective ones in the populations. Number of choosing small n minus K non-defective cones from capital N minus R non-defective cones, which are there. This is in the population and this is in the samples. And this is the number of ways the samples can be drawn of size small n can be drawn from the population, which is capital N. So this ratio is going to give you the probability of X equal to going to be K. A proportion defective in the lot is R by N. Proportion non-defective is 1 minus P, 1 minus R by N. And the mean of this distribution is going to be NP. And the variance is NPQ multiplied by capital N minus N by N minus 1. For binomial distribution, the variance was NPQ. This is the additional part which is coming because here we are not replacing. This is without replacement. And population is finite. Population is not infinite. So the moment I choose a defective ones, probability of getting the next defective one is going to be affected because one defective item has been chosen already. So now the number of defective items has reduced. So the probabilities for successive events are not independent of each other. Now if I take an example, it will be also make things little clear. Example solutions are not difficult. One is, let's say there are 50 bales of cotton is to be processed. In these 50 bales, 3 bales have very high percentage of immature fibers. If 5 bales are chosen at random, what is the probability that none or 1 or 2 or 3 will be found having high immature fibers? The problem is stated. So reading the problem, the first thing is, what are the parameters of these distributions? And you find out the values of those parameters. Here, the items in this case are bales. So how many bales are there? 50. So the population is finite and this is 50. So capital N is 50. Number of defective bales, that is immature fibers which are there, is 3 in this 50. So we write R equal to 3. So non-defective is capital N minus R, 50 minus 3, which is 47. Now how many samples I am choosing? I am choosing 5 bales at a time. So 5. And now interested to know, out of this 5, there will not be any defective at all. That means not a single bale is going to be having immature fibers. So Px is K is going to be 0, This is the formula. We just substitute the values and get a figure which is 0.7239. So if we use calculator, you have to do repeatedly K0, this is the value you get. For K equal to 1, again you have to change these values here, the numbers here. For K equal to 2, also you have to change the numbers here, and you have to calculate repeatedly. But if we go to Excel, you get this function hypergeom.dist, you will get this window. In this window now, you have to choose the parameters. What is the population size? Number in the population is 50, so I have put here 50, the figure. Then in this 50, how many bells are defective? That is 3, we have put 3 here. Then the sample size is what? 5, 5 is fixed. What is I am adding here because I want to know for different values of K. And the K value has to be written here. So here again same way you have to write a column. Suppose the column is E. So this is the value of E1, column 1, this is the value E2, this is for E3, column. So column is fixed and these are the rows, E4, these are the values. Once you have this and then you write E1, when you go to the probability column, you know this, you have to know that how to, how to write. It is automatically going to take, write equal to and then put these values here, it will calculate. You see the value here is 0.7239, this is the figure which is here. And then they will copy and go for the next of the rows, these values are automatically, it will be calculated and the values will be shown. So this will be so fast. And we see here in these situations, the probability of getting no defective bales is maximum 0.72. Only one defective bale is 0.25. Two defective bales is 0.02. Three defective bales is 0.00. So you get the figures and you can plot it if you want to plot it. So with this, we have taken, I think, one more example exactly of similar nature. So just simply substitution. The more problem you solve, the more you will learn. So after going through this, you have to also solve problems. You get a textbook, the problems are there in the end of any chapter, and you keep solving them. You have to practice. Suppose you have to form a team of 8 supervisors from different departments of a textile mill. The mill has 30 supervisors, and 10 of the supervisors are from weaving department. If we are to select randomly the members, what is the probability that the team will contain 2, not managers, 2 supervisors from weaving department? This is what we want to know. And the exactly same way we have to do the calculations. That is, first you find out the values of the parameters, capital N, small n, R, and what is the value of K that we are looking for here. Once we have this, just substitute in this formula, you get a value 0.298. So probability that X is going to be K, where K is 2, that is 2 supervisors from weaving department, out of how many you are choosing? You are choosing 8. Randomly you are choosing. 2 will be there in the team. That probability is 0.298. So with that, we close this particular lecture. And as I said that the learning will be complete once you solve many problems, many numericals. Okay, thank you.